Alrighty, friends, let's take a look at 2.2. We are not really going to be doing a ton of new math. We're just going to be putting some concepts together. So in the last section, we learned about arithmetic sequences, and we talked about how they behave like linear functions by increasing by a constant number or decreasing by a constant number. And then we talked about geometric functions, and that those sequences behave like exponentials. So let's review what linear and exponential look like and how that compares to arithmetic. So these are all pretty important concepts. I would definitely, if you're in my class, I would be highlighting all of these kind of as green concepts that you need to know. And then the majority of our notes will be examples. But you are going to have to kind of be able to differentiate between, let's say, arithmetic and geometric, but then also understand how arithmetic is similar to linear and how geometric is similar to exponential. So you want to be able to understand all those relationships. So these are the formulas that we learned. This one does require that you know the initial term. And if you don't know the initial term, this is going to be the more expanded version, where this is going to be the start term, like the term that you are starting with. And then you are moving towards this like term where you want to stop or end. So if you're going from like term 2 to term 9, you'd have to use this formula. You cannot use the initial term option. Now, if you look at our linear function equations, they look suspiciously similar. You guys are familiar with mx plus b. They do write it as b plus mx here, but same thing. So you can see how these two are really the exact same thing. You have an initial value, and then you have a rate of change attached to your variable. Here we have an initial value, a rate of change attached to our variable. So those two are equivalent in nature mathematically. And then this is the more expanded form when we don't know the zero value, because keep in mind here, the b is what you had when you put a 0 in for x. And so here, this a sub 0 is what you got when you put a 0 in for your function. So here, you're going to have some other value than the 0 value. So you can see the similarities between these two, where here is my function, this is this number I'm starting at, my rate of change, which would be my common difference, and the change in my x's. So it's just important to kind of understand how those are the same as what we've learned in the past. Geometric, on the other hand, are exponential, meaning that you have your variable in the exponent. And you don't have an increase that's adding and subtracting. You have an increase that's multiplication, repeated multiplication, which is where exponents come from. So these setups, these equations are the same as what we learned when we have learned exponential functions in the past, where b is raised to a power versus r raised to a power. The growth factor we talked about in exponential functions is essentially the same mathematically as the common ratio we talk about now. So this is, again, the version where we don't know the 0 value or the initial term, and so we have to adjust our power accordingly. So those are not new items. Those are just looking at how they relate. So keep in mind that when you have a linear function, you're going to have this format, and this is important to look, because this is how you determine it. Over equal length input value intervals. What that means is you have to have the same distance between the x values. So you have to have a consistent distance in between there. And then the output changes at a constant rate. So this is going to be an important concept to tie together, that it will be linear if you have over equal length input value intervals a constant rate of change in your y's. So your y's are basically going to be going up or down by the same number every time. So constant rate simply means the same number. And that change in y is based on addition. Sometimes subtraction, but same as adding a negative. So this is all linear, which is all arithmetic. So subtraction and addition were the ways we traveled from term to term. And then the kind of flip side of that is going to be, what if I have an exponential function? Keeping in mind that this is equivalent to arithmetic, this is equivalent to geometric. So again, over equal length input x values, so you do have to pay attention to the x values. The output values change what we are going to call proportionately. So if you're going to change proportionately, you are changing by a multiplier. Multiply, that's terrible. That's not legible to even me, and it's my own writing. Which is not surprising, because you would have a multiplier in exponential and geometric because you're multiplying, like having a common ratio. So the change in the base is based on multiplication. So this is not telling you anything you don't already know. You already knew that exponentials, which are geometric, change by a multiplier. They might use b in this equation, but we used r in our other equations. Over here, they might use m as the slope. Well, we used, like in our original ones up here, we used the common difference. So they're just showing that they're just different terminology for the same concept. So if you have 2 points, 2 xy points, you can write the equation of a linear function and an exponential function, arithmetic or geometric, because really they're all the same in nature. So this page is going to be super essential for you to have a grasp on for your AP test, and obviously for any upcoming assessments in class. The rest of what we are going to do are going to be examples kind of applying those concepts. So let's make sure that we know, what does this all look like in action? So let's take a look. Tables. We have done tables before. It says select values of several functions are given. For each table, determine if it could be linear, exponential. Okay, they are not asking arithmetic or geometric, but they could be. Now, we have to make sure before we start that we meet this condition that over equal length input value intervals. All that means is that your x's are changing by the same amount, because if they're not, you can't apply this process, and they are. So I'm just looking at that saying, yep, these are equal intervals. Now I'm going to look at the change in y's. These are going down by 2 through subtraction, down by 2, down by 2, and down by 2. So in my notes where it says output values change at a constant rate or a proportionate rate, I have to look and see. -2, -2, -2, -2, that is a constant rate. They are the same number. So I can conclude that these are linear. This would be a linear function. And it wants me to give a reason for my answer. So I have to explain that my output values, which are those f of x's, my output values change at a constant rate. They constantly go down 2. So, and you could say, you know, of -2 if you wanted to, but that is over equal intervals of x values or inputs. So you have to check that those inputs are equal values before you can make a determination. So when I look here, I check that my x's are doing the same thing, and they are all going up by 1, so I'm at least good to go. When I look at this, I see that this increases by 1, this increases by 3, this increases by 5, and this increases by 7. So it's definitely not linear, because obviously 1 and 3 and 5 and 7 are not the same. I can see a pattern, but they are not proportionate. They are not changing like by a multiplier. I can tell what the next one would be, right? It would go up by 9. But since it is not a constant value and it's not proportional, meaning that I'm not multiplying, this is going to be neither. It has a pattern, but not every pattern has to be linear or exponential. They could be many other things. So here, I would just say that the output values are neither, so they are not constant and not proportional. I can't spell that, apparently. So they are not the same, and they are not multipliers. And this is all over equal x intervals, because you want to make sure you are recognizing that you understand the need for that. So if I look at my next table, I double check. These are going up to, up to, up to, up to, so I can check that those are equal x intervals. Here, these are not going up by multiplication. Here, this is going like by a product of 2, and then this is getting doubled. 4 to 8 is getting doubled, and 8 to 16 is getting doubled. So that's a multiplier. That is going to be proportional. That's not constant. It's not just going up by 2, because you can see that if you look at how much it's going up by, this is only going up by 1, but then this is going up by 2, but then this is going up by 4, and so on. But there's a multiplier to go from one term to the next. So that's going to make this one exponential. And the reasoning is going to be that those outcome values change proportionately. And I just love writing this word because I can never spell it. Proportionally. Okay. Meaning that there's a multiplying pattern. Okay. And again, that is happening over equal input intervals. So you're saying, I recognize that my x's were in equal intervals, and now I see that my y's are multiplying to become the next y. Checking on this last guy, up by 5, up by 5, up by 5, up by 5. So check, I have equal intervals. Here, if I look at this, this is half. 40 is half of 80. 20 is half of 40. 10 is half of 20. And 5 is half. So you might think you're dividing by 2, but keep in mind we have to use an R value, like a multiplication. So dividing by 2 is the same as multiplying by 1/2. So this one is again going to be exponential. And my explanation is going to be the exact same, and I'm not doing it because I don't have enough room, sorry. And you cannot write same. You have to actually explain. But you would have the outcome values change proportionally. Last time they were doubling, this time they're multiplying by 1/2. But it's still true that they are proportionate over that equal interval values of x or inputs. Okay, so that's how we're going to deal with the tables. How are we going to do these problems? A wild rumor is spreading that Mr. Timo won 3rd place in the World's Strongest Man contest. The number of people that have heard the rumor can be modeled using a geometric sequence, okay, where 43 people had heard the rumor on day 3 and 140 people had heard the rumor on day 6. Okay, so what do we know? And then it's asking, according to the model, how many people to the nearest whole number, pay attention to that, have heard the rumor by day 10. All right, so what do we know? We know it's a geometric sequence. We know that our third value is 43, and that our what's the other one that we know? So on day 3, it was 43, and then on day 6, it was 140. So that's the information they gave me, and it says how many are on day 10. So that's what I'm ultimately trying to find. But in order to do that, I have to find an equation. And in order to have an equation, I'm going to need to find that R value. So let's do that. Also, let's dig around and see if I can find a calculator that works, because it looks like I might need some help with that. Alrighty, so what do? Well, we need to use our formulas, and we do not have an initial value. So I'm going to be using that any term I can find from a starting term, applying my R, n minus k times. That is my formula. I use it for pretty much all things geometric. So I would say, well, I'm gonna change these to g since it's geometric. To get to the 6th term, I'll start at the 3rd term. I will apply my common ratio 6 minus 3 times, because that's how many spaces I'm gonna have from the 3rd to the 6th term. What is the 6th term? 140. What about the 3rd? 43. That will give me R to the 6 minus 3, which is 3 power. Now I can keep solving to get to R. So if I do 140 over 43, that does not reduce at all. And to get R alone, I'm going to need a 3rd power, cube root, I mean. So I need the cube root of this entire thing. So on your calculator, you do, under your math button, have a cube root key. So if you cube root that whole fraction, 140 over, or you can even just cube root the answer if you have it still on your screen. But get a cube root for that whole thing. You're going to have an R value of approximately 1.482. If you change it into a fraction, it's not changing it into a fraction, so we'll leave it. Okay, so that is my R value. Great. So my formula to figure out other terms is going to be to find any term. You can start at term 3, which was 43. You can use this R value to the n minus 3 power, because this was my 3rd term, 43. So for me to find the 10th term, I'll have 43, and then this answer for my R value to the 10 minus 3. So I'm going to put into my calculator this business, and I'm going to get a 7th power. So if I do that, I'm ending up with a 10th term of approximately. Now be careful, because it says to do the nearest whole number, and a lot of people miss that on the quiz if it says integer or whatever, because I'm getting this, but that whole number is closest, that whole number is closest to 676 people. So that is the same process as we've been doing. And they could have called it exponential, and we would have done the same math, but they called it geometric. All right, example 3. A large theater has rows of seats where the number of seats can be modeled by an arithmetic sequence. Terrific. The 5th row has 31 seats. So that tells me the 5th row has 31 seats. The 11th row has 49. I'm just supposed to determine how many seats there are in the 25th row. Well, I can't do that until I have an equation, and I can't have an equation until I find the common difference. So let's figure that out. I'm going to use my ending term, my starting term. I'm going to figure out my common difference through this formula. That was the one we've been using since they said it was arithmetic. Okay. I'm going to end at the 11th term, start at the 5th, add my common difference, 11 minus 5 times. But I know the 11th term is 49. I know the 5th term is 31. I do not know the common difference, but I know I'll use it 6 times. So if I keep going in my solving, I end up here with 18 equals D times 6. So my common difference is going to be 3. And that's positive, so I'm increasing the number of seats I have. Okay, so now I need a general formula, and when I do a general formula, I leave the ends. I'm gonna start with, it doesn't really matter which one, so I'll just go ahead and start with my 5th row. I'll just use this one. So if I'm starting at 31, I'm gonna add my common difference of 3, n minus 5 times, because this was a sub 5, sorry. Okay, and then I'm being asked to find the 25th term. And you could have distributed the 3 and simplified it, but you also could just put that 25 in here that you're looking for. And I would end up with 31 plus 3 times 20, essentially. And so the 25th row will have 91 seats. So you're just taking the information out of its kind of application setting and doing the same math that we've been doing the last couple of days. Let's knock out these last 2 and be done. Immediately following the AP Pre-Calc exam, memes are created and shared online. The number of people who have seen them can be modeled by a geometric sequence. So now you don't have any doubt about what formulas to use. 1 hour after the exam ends is hour 1. Okay. At hour 3, a total of 2,500 people have seen this meme. Okay. So this is going to be 2,500. And then 20,000 had seen it by hour 6. So the 6th number would be 20,000. Using this model, how many will have seen it by hour 10? Okay, so same exact process. It's geometric in nature. So to get a formula, I have to have an ending and beginning term, an R value, and the difference between the N and my K. So in this particular problem, I'm going to go from term 3 to term 6, because those were the ones that were given. To do so, I will need to use my R 6 minus 3 times. G3 is 20,000. I'm going to actually put this over here so I have room to work. G3 is 20,000. G6. And that's going to equal G3, which is 2,500. I do not know R, but I know it's going to be to the 3rd power. So when I divide my 20,000 by the 2,500, that is going to turn into 8 equals R cubed. I'm going to use my cube root to find out that R is 2. Okay, I don't have a formula yet, but I can get one. So now I'm going to write my general formula, meaning I leave all my ends in place. I'm going to go ahead and start from A sub 3 at 2,500, and I will apply my common ratio that I just found of 2n minus 3 times, because this was A sub 3. So if you want to know the 10th term, I'm going to plug in a 10 right up here, and I'm going to end up going to my calculator and taking 2,500, and then in parentheses 2 raised to the 7 power. And I am coming up with, at that point, 320,000 people will know or will have seen it. Same math, different setting. All right, grand finale. Across the U.S., there are approximately 45,000 flights each day. In certain simulation, the total number of flights that have begun across the U.S. n hours since midnight on a given day can be modeled using an arithmetic sequence, where 12 a.m. is represented by n equals 0. That's a lot. The total number of flights that had begun by 5, okay, so that is going to be our A5. And that is going to be 11,750. And by 11, which will be 11 hours after midnight, that would be 22,250. Based on the simulation, how many flights will begin by 12? Okay, I have to, or 6. 6 p.m. is going to be 18 hours after midnight. Look at me thinking. And now, my friends, we're doing the same exact thing as we've been doing. We need to find the common difference so we can build an equation so we can plug in 18. It's arithmetic. So our last term that we're going to go to will be our first term plus the common difference, n minus k times. That's my starting block all the time. I have A5 and A11. So I'll be starting at A5. I'll be going to A11. I'll be adding the common difference, 11 minus 5 times. What can I plug in? I know that A11 is 22,250. I know that A5 is 11,750. I do not know the common difference, but I know that I will use it 6 times. So now I'm going to do a little bit of Algebra 1 to determine where I'm at with that. 22250. All right, so here I've got 10,500 equals 6 times the common difference. So if I divide that by 6, I am getting a common difference of 1,750. Great. It doesn't ask me that anywhere, so I just need to know that I need to know that, so that I can go ahead and say, now I'm going to write the general formula where I only leave the ends. So this and this. I got to start somewhere. So I'm going to go ahead and start at the 5th term they gave me. So 11,750. I'm going to add the common difference that I just got. And that's going to be n minus 5 times because this was term 5. And you could have used term 11 and then put the 22,250 here. It won't matter. In the end, you would get the same thing, but then you would have an 11 here. So I'm just going to put, or you could have said, hey, I'm starting at my 11th term. I'm still adding the same common difference, and then I'd be here. Either one of these is going to lead you to the same answer. Since this one's on the bottom, I'll just go ahead and use it. To find the 18th term, I'm going to go ahead and plug in 18. I don't have to simplify the equation because it really didn't ask me to show the equation. It just asked me to come up with that, that 18th value. So now I am doing some maths on my calculator. 22,500 plus 70, 50 times 7. Why does he have a different answer? All right, so I am getting that 18 would have 34,750 people. Hang on, I'm using the other one real quick. Okay, so all of these problems that we did in this video are the same. You are every single time deciding if it's arithmetic or geometric simply based on their wording. You're using the kind of basic formula. Sometimes you have to find the R and find the D based on what they gave you for examples, like the 2 points. Then you write your general equation, and then you use that to find the prediction that they're asking for. So really dig into doing these and feeling comfortable with these, because at the end of the day, this is what you have to be able to do in those arithmetic and geometric, which are the same as if they ask for linear or exponential. And we'll dig into that more in the future. Thanks, guys. Bye.